Okay, so I'm going to start the review of the interim exam. This first question basically tests your understanding of what's the null hypothesis, what's the alternative hypothesis, and what kind of errors can be associated with them. So let's read through them here. You'll see the answers. Actually, in this view, you actually see the correct answer displayed as we go through it, or what range I gave it, and so on and so forth. It's a numerical answer. You'll see what range that I made acceptable and so on. Okay, so let's start with the first one. Okay, and hang on a second. I see some questions. We're going to go up the chi-square table, and when are you going to upload the chi-square table and ANOVA table? Do you mean the reference table for chi-square and ANOVA, like the one that I usually use from Agresti from the other textbook? Or do you mean, oh, okay, I could do that. That's not a problem. It's a good, those are particularly good reference tables, I think. I think the format that they have is good. I did, if you notice, I uploaded videos of my going through that exercise a little bit more slowly and deliberately that we did for analysis of variance. I'm going to do one for chi-square also. Well, the chi-square example we did in class, I think worked out pretty well. But the ANOVA one, I really rushed through, made a couple of math errors in and stuff. So I think it's more appropriate to use those. Also, using the same data, using SPSS to solve for analysis of variance, and also to do the post hoc tests using SPSS. You see those videos linked to announcements on Blackboard. Okay, but I will upload those reference tables so you have them. And in fact, maybe I'll make a folder kind of all the reference tables that you might want to have. Okay, so at any rate, let's take a look at this. So, first question, match following decisions with the corresponding statistical terminology. Okay, and basically what we're looking for, what's a type 1 error, what's a type 2 error, what's a correct rejection and null hypothesis, and what's a correct acceptance of the alternative hypothesis. Okay, so normally the null hypothesis, unless we have enough evidence to reject it, we fail to reject the null hypothesis. In other words, our objective in proving something is to show that they're different, show that group A is different from group B, or some intervention works, or so on and so forth. So our null hypothesis is something that we're interested in disproving. So if we fail to do that, we just simply fail to reject the null hypothesis. If we manage to do that, then we reject the null hypothesis and we accept the alternative hypothesis. And we can make errors. You know, there are two types of errors. We make type 1 and type 2, in which we could either incorrectly reject the null hypothesis and accept the alternative, or incorrectly incorrectly fail to reject the null hypothesis when in fact there is a difference between the two groups. Of course, the first error, called the type 1 error, the first one I described, the former one, is considered a worse error, because in that one you're saying that some intervention, some drug, there is some difference between two groups that you feel that you've proved with adequate certainty. And usually people act on those things. They sell the drug, they take the drug, they spend money on the intervention or test, and so on and so forth. So that's considered a worse type of error. Type 2 error typically means that you haven't proven what you wanted to prove, that there's a difference or an advantage to an intervention or something like that. So, but you always have the opportunity that if there is what you believe to be evidence that that's true, you can always go back and redo the study or do it with a larger sample size or something like that. So let's read these. Concluding that infants who ultimately died of SIDS have lower birth weights than other full-term births, when in fact there's no difference. Okay, there's no difference. So the null hypothesis is true. However, you've concluded that there is a difference in birth weight. So you've incorrectly rejected the null hypothesis. So that would be a type 1 error. Incorrectly concluding that the birth weight of infants who ultimately died of SIDS is the same as other full-term births, when in fact there is a difference. Well, you've concluded that the null hypothesis, you failed to reject the null hypothesis because you've concluded that the birth weights are the same, but there is a difference. So that's a type 2 error. Okay, correctly concluding that infants who ultimately died of SIDS have lower birth weight than other full-term births when this difference does in fact exist? Well, that's correctly rejecting the null hypothesis. And finally, concluding that the birth weight of infants who ultimately died of SIDS is no different than other full-term births when there in fact is no difference. Concluding that the birth weight of infants who ultimately died of SIDS is not different, there's no difference, when in fact there is no difference. Okay, and that's correctly accepting the alternative hypothesis, right? Our alternative hypothesis, well, hang on a second here, let me just think about this for a second. There's no difference, correctly assumed there's no difference, that birth weight of infants who ultimately died of SIDS is no difference when in fact there is no difference. That's correctly correctly accepting the null hypothesis. I don't like that phrasing because really what you're doing is you're failing to reject the null hypothesis. They phrased it that way there because in fact it's more of a positive situation than a negative. Okay, so in that case, the null hypothesis is true, and you are correct in saying the null hypothesis is true. Okay, everybody okay with that? There are a few people that had a little issue with that, mostly I think with type 2 errors, defining what type 2 errors are. But basically, that's when you fail to reject the null hypothesis when in fact there is a difference. Okay, for a given alpha level, as sample size increases, the critical value for T also increases. So what do you guys think about that? Well, in fact, that's false, isn't it? And you know why it's false? Because as the sample size increases, if you look at the T table, the critical value of T goes down as the sample size gets bigger. In fact, when the sample size gets big enough, it goes all the way down to 1.96. So for a smaller sample size, the critical value of T gets larger and larger. You need T to be bigger for a small sample size to be able to reject the null hypothesis than you do for a large sample size. And let me see if I have a T table handy here, and you can just confirm that for yourself. Degrees of freedom is just the sample size minus 1. As the sample size increases, what happens to T? T goes down, gets smaller and smaller. So you can confirm that for yourself there. Okay, in fact, you could have just on a test confirmed it by looking at the T table. Okay, next, check all that are true about the T distribution. And I gave away that there are actually 3 of them that are true, but let's see what's not, what is true and what isn't true for each of these statements. First statement, there is a single T distribution for all sample sizes. Well, if that were true, we would need a T table, right? So there's a different T distribution for every different sample size. Now, we don't bother to actually have a page like for the Z-score for every different sample size. Instead, we just have a line that gives you the important critical values. But there is literally a separate distribution for each sample size. Next, the T distribution. So that one's false. The T distributions have wider tails than the standard normal distribution. That's true. That's the reason why the T has to be further out. The T distribution is more spread out. There's more area in the tails than in the normal distribution. That's why you need a bigger difference in T, a bigger T value, further away from the mean in order for you to get only 5% left in the tails. Okay, so that's true. It can be used when, again, talking about the T distribution, it can be used when population standard deviation is estimated from a sample. Well, in fact, that's most of the time when you will use it, right? You don't need a T distribution if you know a population. So, or when the sample size is small, you especially need it to make up for that increased variability. So that's true. That's really that's really the function of the T distribution, is to give us an idea of what the standard error should be for different sample sizes, or what the critical value has to be for different sample sizes. When using the T distribution, we assume that samples are drawn from an approximately normally distributed population. Now, the key answer there, I'm sorry, not sure. That might be volume has decreased in the audio. Hang on a second. Let me see. Hello, hello. That looks okay on my end. Hmm. Maybe I'm looking away. Okay, good. Let's see. Where was I here? Uh, when the t distribution, when the t distribution, we assume samples are drawn from an approximately normal distribution. The key now, you know that one of the things that we said about the central limit theorem is that when you take repeated samples from the same population, then you don't necessarily have to have a perfectly normal population, normally distributed population, in order for your assumptions for the central limit theorem to work. However, when we use the t distribution, it is important that the original population be at least approximately normal, not to be terribly badly skewed. Okay, I think that's probably in one of the slides, one of the PowerPoint slides. And finally, that's true. Finally, the t distribution can only be used for small sample sizes. Well, in fact, we know better than that because SPSS, we know the t distribution is available. So if I can't find it here, there it is. See, the t distribution goes all the way up to 20 sample size of 20, 28, 30, 80, 100, and at infinity, it's equal to the same thing as the z distribution. So you can use it for very large samples. In fact, SPSS always uses the t distribution, no matter what the sample size is, rather than just assuming that it's the same as the z distribution, which is really only absolutely perfectly true at infinity. So correctly, SPSS uses the t distribution for any sample size, but it's particularly important for small sample sizes. But to say it can only be used for small sample sizes is wrong. So the middle three here are the ones that should have been checked off. Okay, problem so far. Anybody want to dispute that? Good. I like it when nobody wants to dispute it. Okay, when I'm not always right either. You know, you've seen that. I've demonstrated that plenty this semester. When standard deviation is estimated from a sample, which distribution will provide a more reliable result for testing hypothesis and confidence interval estimation? When it's drawn from a sample, when it's estimated from a sample, which one gives us a better, more reliable results for hypothesis testing? Well, the t distribution does. T distribution, again, is designed for helping us understand the distribution of sample means when we have to depend on the sample to give us the an estimate of the standard deviation of the population. Otherwise, we would use if we knew the population standard deviation, we would use the normal distribution. Okay, let's take a look at a true false here. A 95% confidence interval determined from a sample captures the values for 95% of the individuals in the population. Okay, a 95% confidence interval determined from a sample captures 95% of the individuals in the population. Now, when we calculate a confidence interval, we're not getting the range for the individuals in the population. We're getting a range for an estimate of the mean. In other words, an estimate of 95% of the sample means if we took repeated samples of that size, or even more correctly, 95% certainty that the real mean is between those two values. That's depending on the sample size. That's anywhere from a narrower range than 95% of the individuals, or for a large sample size, a much narrower range than 95% of the individuals. So that's a false there. The t distribution converges to a normal distribution when the degrees of freedom increases to infinity. Okay, and that's true. We just saw that, right? Okay, if you look at this, is when we get to infinity, well, then the t distribution is the same as the normal distribution. And the shape, the bell curve shape, is exactly the same as the normal distribution. It's not bigger in the tails the way it was in that previous problem. Okay, let's do a calculation. You calculate t-score for the comparison of two sample means. Will you be more likely to reject the null hypothesis if you choose a one-tailed test instead of a two-tailed test? A lot of people got this wrong, okay? And the answer is yes, you're more likely to reject the null hypothesis if you choose a one-tailed test. I'm going to illustrate that because that's kind of an important concept. Let me bring my notepad up. Okay, I'm going to need that. Hang on a second. Drop my pen. Okay, here is my distribution of all my sample means. Right? And here is where I believe the mean of the population to be. Now, let's say we're calculating a t-score, number standard deviation. The t, it's usually, if it's a very large sample, we'll call it a z-score. If it's a sample less than 30, we'll call it a t-score. We're going to calculate that. And that's going to be equal to x bar, whatever it comes out to, minus mu over the standard error. And that's going to be the distance between, basically the distance between the mean and that value for that particular sample size and standard error, and the distance between these two values. In other words, how many standard errors apart is this? Okay, so let's say that t winds up being exactly 2 standard errors apart. Okay, so now if I look at this, 2 standard errors might be out here somewhere, right? Well, when do I reject the null hypothesis? Well, this distribution of all the sample means, what it represents is the probability of getting a sample of size n, whatever it happens to be for this particular distribution, getting a mean of size n, what the probability is for different distances from the real population mean. Okay, so in other words, if I wanted to be 95% certain that that the mean from our sample came from a different population with a different mean, right? If I wanted to be 95% certain, I would have to make sure that only 5% of the time would I get a result that extreme, that far from the mean, from the population, from a sample of the same size from the population that I know the mean for. Okay, what does that mean? That means you have to be so far apart that there's only 5% of this area of this distribution left. Okay, so if we have the normal distribution or t distribution, it doesn't matter which. If I do a two-tailed test, right, it means that I don't know if x is going to be on this side of the distribution or if x is going to be on this side of the distribution. I don't know if it's going to be less than mu or greater than mu. So I have to account for that 5% at both ends of this distribution. So a two-tailed test, right, means that in order to reduce my error to 5% chance, I have to put 2.5% of that here and 2.5% of that here. So if I assume that we're talking about z now for z or very large sample size, if I say z is equal to 2, well, I would have to be that far out. I would have to be 2 standard deviations out to get 2.5% here and 2.5% here. We know that from our understanding of normal distribution. I have to be that far out in order to get only 5% chance of being wrong, having a value come up either too low or too high to be part of this population, but in fact be part of this population, right? In other words, be wrong if I reject the hypothesis. So it'd have to be way out here. But now think about this. If I made the assumption that x bar can only be a positive number, right? And that it can only be bigger than mu, right? Or rather the z or the t value for this x bar can only be a positive number, all right? And so it's only a one-sided test. If I made that assumption, then I could put all 5% of my possible error here. And if I put all 5% on one side, well, now my critical value of t doesn't have to be as big. In fact, all it has to be is 1.64 instead of 1.96. Okay, that's why the answer to that question would be yes. You're more likely to reject the null hypothesis if you choose to do a one-tailed test than if you do a two-tailed test. That's also why I've been telling you that a two-tailed test is more rigorous and more conservative, right? Because it's harder to reject the null hypothesis if you do a two-tailed test. So that's one of the reasons why we use that convention, even though a lot of times we might really suspect that we could do a one-tailed test, that the difference can only be in one direction. I can't see my answers. I thought it was open. I think, I'm not sure, but I think you might not be going into the right spot because it should at least tell you which ones you got right and which ones you got wrong. So anybody help her out with that? Because I can't see her view of it or his view of it. Who's KB, by the way? Click on your score. Everybody agree with that? Okay, Karen. Everybody agree with that? You click on your score and it didn't work for you? Any other contributors there on what you might do to see which ones you got right and wrong? Some people seem to have problems on it. I'll check that out tonight, see what I can do. I'm going to set up a kind of like a fake student. Nor on OK. I'll try and set up a fake student and see if I can't get it to show us what the issues were, or try and figure out what you might have to do procedure-wise to do that. Okay, well, let me move on, and I'll take a look at that later on tonight. Okay, so the next one. We got that one, right? Okay, so the answer for that is yes, not no, and you have plenty of information. Okay, the result of a t-test comparing means with alpha is equal to 0.05 results in a p-value of 0.07. Which of the following is the most appropriate conclusions? Okay, well, what this says, the p-value is the probability of getting that result if it's part of this, if the two populations have the same mean, if the two samples or the sample and the other population have the same mean, that's the probability. That p-value represents that the area that you're at with whatever t-score you got is leaving 7%, leaving enough area under that curve to be 7%. We only want it to be 5% or less. So in that case, since the p-value is greater than 0.05, not less than 0.05, we fail to reject the null hypothesis. Okay, we don't accept the null hypothesis, we fail to reject it. Okay, let's see. By how much must the sample size be increased if the width of the confidence interval is to be halved? A lot of people got this wrong. I would say probably out of 30 people, maybe only about 5 people got, maybe at most 5 people got this right. I'm gonna show you what the reasoning behind that is, and hopefully it'll make sense to you. Let me get my notepad up here again. Okay. Let me get a new page here. Okay, how do we calculate the confidence interval? Well, the confidence interval is equal to x bar plus or minus my margin of error. Remember, we call the margin of error. What is the margin of error? The margin of error is, I'm going to make believe it's a big sample for our purposes. It really doesn't matter. Since sample size was not relevant, we're just talking about large sample size. For whatever sample size it is, we're gonna talk about. I'll stick with 1.96 for our purposes. 1.96 times the standard deviation over the square root of the sample size. Okay, so now if I make the sample size bigger, right, then this number is smaller, right? And if I multiply it by 1.96 or whatever t happens to be, then this whole number, the margin of error, is smaller. So what does that mean? that means that the amount you're adding and subtracting to x to get the confidence interval is smaller. So as the sample size gets bigger, my confidence interval gets narrower for the same percentage, right? So sample size of 50 might be that wide, and the sample size of 100 might be that wide, because this bigger number divided into the standard deviation makes this whole number smaller. When you multiply it by 2, then the result, the margin of error, is smaller, and you're adding and subtracting that much. Let's take a look at, but the only problem is it's the square root of n. So if this were not the square root of n, standard deviation over n, then if you doubled n, you would have this whole fraction, and you would have the margin of error, right? But it's not just n, it's the square root of n, right? So in order to have the margin of error, n has to be four times larger, not twice as large. I'll give you an example of that. Let's say that we're looking at the standard deviation is 10 over the square root of n, right? That's our standard error. Let's see what happens if I put different size n's in there. Let's say I put in a sample size of 25. Okay, so that's going to be equal to 10 over the square root of 25. Okay, that's going to be 10 over 5, which is going to be equal to 2. Well, now watch what happens if I make the sample size 4 times larger. 10 over the square root of 100 is equal to 10 over 10 is equal to 1. And since I've halved the standard error, I've halved the width of the confidence interval. Okay, that's why the sample size has to be 4 times as great to have the width of the confidence interval. Okay, it's a little tricky, right? That might have been a little bit of a curveball, but do you guys get it now? I mean, does it make sense to you? It's not going to turn up again, so I promise not to do that one again, right? But again, you get the idea there that as we increase the sample size, we don't really get that big a return. We really have to increase the sample size quite a bit to really reduce the confidence interval. It's not just a linear relationship. But we know not only as we increase the sample size, does the confidence interval get narrower, but also we really have to increase it quite a bit to get a significant narrowing. Okay, and that's because it's an inverse square rather than directly inverse. Okay, let me get this out of the way and go back. Okay, now I gave you a formula for this one, so you didn't have to dig around. Time magazine quoted a poll performed in 2008 of 1,000 Californians, in which 18 out of the 100 Californians said that they were vegetarian. Construct a 95% confidence interval for the true population proportion of vegetarians. And then ask you for what the lower bound is going to be and what the upper bound is going to be. Okay, so let's apply this formula. Okay, first of all, we always use the z-score when we're dealing with calculating a confidence interval or t-score for a proportion, because our first rule is that there has to be at least 30 people, 15 in each side of the outcome. Okay, and I'll show you that we have that. Okay, so let's see. Okay, n is equal to 100, right? And 18, I'll call that 18 are successes, right? 18 people are out of 100 are out of 100 randomly selected people are vegetarians. Okay, so let's take a look at that. That means that 82 people are not vegetarians, non-successes or failures, right? So you got 18 in one group, 82 in the other group. So we have our 15 plus in each group. So we can go ahead and use the z-score. So z is going to be equal to the proportion in our sample. I'll call that p cap, right? Plus or minus 1.96, just like a mean, right? Times the standard error. Okay, now the only curveball here is the standard error is a little bit different. How the standard error calculated? It's the square root of p times 1 minus p over n. Now, the only P that you have in this question is the P, the proportion of Californians that are vegetarians from your sample. So that's the only one that we're going to be able to use. So let's see what the standard error is going to be. Standard error is square root of P times 1 minus P over N. Right? And that's going to be equal to 0.18 times 0.82 over, sample size was 100. Okay, and we take the square root of this whole thing. So let's get our calculator out and do that step by step. Okay, since this is all divided and multiplied, it doesn't matter which one I do first. So I'm going to 0.18 times 0.82. I'm going to go ahead and resolve that. Comes out to that, divided by 100. Hope I pressed the right one there. And it comes out to 0.001467. It looks like a very small number. However, now we have to take the square root of it. When we take the square root of a fraction, it comes out to be a bigger number. Square root, and it comes out to be 0.0384. So if I go back here, 0.0384 plus or minus 1.96 times 0.0384. So it's going to be, the proportion is 0.18 plus or minus, and now let's resolve that 1.96 times 0.3084. Okay, so let's see what we get. Times 1.9, oops, oh no. I'll have to do this up, 0.38. I'm going to do this way, 0.38, 0.0384. 384. I lost part of it, but that's okay. Times 1.96 equals about 7.5%. I'm going to put that into memory, and I'm going to clear the whole thing, and it's going to be 0.18 minus, I'm going to recall it from memory. Oh no, I did it wrong again, didn't I? Okay, 0.0384 times 1. It's not cooperating. Yeah, it's so hinky to use a calculator with a keyboard and a trackpad. 0.0384 times 1.96 equals this, memory plus. Okay, now I'll clear it. Okay, 1.96, excuse me, 0.18. 0.18 minus our margin of error, which was our 1.96 times 0.0384. Recall memory is equal, oops, that came out wrong. 0.18 minus, recall memory, equals 0.105 roughly. Okay, and let's see what I took for acceptable answers for that. It's 0.105. It's 10.5%. It's our lower range, right? And I said, oh, you could go as low as 8% or as high as 12.5%. Okay, and still get marked correct for that one. So I gave you a pretty good range on that. What about the upper range? Well, the upper range we're just going to add the margin of error. Let me clear it. 0.18 plus, I'll recall our margin of error is equal to 0.255. And that's what we have. And again, I gave you a 2% range for the margin of error. Could have been 0.23 or 0.27. Now, I did go back, and a lot of people, for one reason or another, gave me a right answer here, said 0.105. And then they went down here and put 25 and called it a percentage rather than as a number. So, oh, you know why? Because it says it right there. I went back and I corrected that. I gave everybody credit for doing it either way, 0.25 or 25%. That's because I didn't edit that part out. I thought I had went back and corrected that, but I guess not on that. I didn't do it on both ends of the question like on that one on the 10 and 11. Okay, so that seems pretty straightforward, right? And it's not much different than what we would do if we worked with a proportion now, except now we would treat this like we would do proportion 1 minus proportion 2 over some pooled proportion that would represent the bottom of our fraction, and square, our standard error, which would include some pooled proportion. And we have a formula for that. And that's what would wind up on the test. I'm going to set up another session here. We're going to go over problems like what might show up on the test as well. Calculate, okay, Time Magazine quoted a poll performed in 2008 of 100 Americans in which 18, did I just repeat that myself? Yes, I did. Let's go to the next one. Nutritionists prepared daily vitamin doses for patients at a care facility using existing measuring equipment. Known by extensive monitoring that the dosages of vitamins prepared using this method average 800 units. The facility is considering new equipment but does not want to change the dosage rate of vitamin D. Using the new equipment, the facility has nutritionists prepare 16 doses. They want to know if it's measured out, if it really gives you the same average as what they were getting before. Sometimes you might get 799, sometimes 802, and so on and so forth. But I'll make sure that whatever technique and equipment that they're using, that they get the same average dose. They found that the average dose is lower, 770. It's different than it was before. But is that difference due to chance for just those 16 samples? And if you'd done another 16, it would have been greater than 800, right? Or is it due to an actual difference in the way the equipment works? With a standard deviation of 30. Okay, so this is a pretty straightforward problem where we are doing basically a single sample t-test. And a single sample t-test really kind of involves a confidence interval. But let's find out if our confidence interval includes 800 or doesn't include 800. So what would our confidence interval? We know that the mean for the existing equipment, based on our history with it, right? The population mean, the mean for all the samples is 800. Now we want to know if the mean for the new equipment is different than 800, and in fact, we have to determine that based on only 16 samples. We want to know if that's enough information. So now we have to find our confidence interval for the true mean for the new equipment. We know that the mean X bar is 770. We know that the standard deviation of the sample of 16 doses is 30. And we want to find our 95% confidence interval. Let's go ahead and do that. Okay, get rid of that. Okay, so our X bar is equal to 770. Standard deviation is equal to 30. Our sample size is equal to 16. And our standard error now is going to be equal to 30 over the square root of 16, which is 30 over 4, which is, let's see, that's 7.5, 7.5, right? I think I got that right. Okay, so let's go back here. So now I want to calculate my confidence interval. So all right, my confidence interval. Now my confidence interval is going to be equal to X bar plus or minus. Well, now I have to have a t-value, don't I? Because the sample size is only 16. I can't use z. So our t-value for alpha is equal to 0.05, two-tailed actually over 2, 0.05 two-tailed, times the standard error. It's going to be our confidence interval. So X bar plus or minus, I'll leave t out for the moment, our standard error is equal to 7.5. So now we have to find out what t is, right? And in order to find out what t is, we have to go to the t-table. Let's see if I can't find it back here again. I have it on the desktop in the back. Here we go. So let's find our sample size is 16. So our degrees of freedom is equal to 15. So for 15 degrees of freedom, if we want to have a 95% confidence interval, 2.5% in each tail, 5% in the two tails together, right? If I want to find out, I want that confidence interval, for t, I have to use 2.131. Again, wider than it would be for the z distribution. 2.131. Okay, so x bar is 770 plus or minus, and let's resolve this. Okay, 2.131 times 7.5 equals 15.98, roughly 16. I'm going to clear memory here, and I'm going to put this into memory. So now that's our margin of error. So let's take our 770 and subtract that from our margin of error from 770. It comes out to 754. Okay, let me just write that down. And our upper range for our margin of error, upper range for our margin of error, let me get this back, going to be 770 plus, yes, it's open book. I love the way you guys answer your own questions back there if I get distracted. It's open book. And this is going to come out to be roughly 786. I'm going to call it 786 for our purposes. Okay, so we're 95% certain that the true mean for the new equipment is between 754. Let me make sure I got that right. Yep, 754. I gave you a buffer of 5, and the other 786 gave you a buffer of 5 on that also. The upper range is that. Okay. Okay, and in a second, so our 95% confidence interval is between 754 and 786. So now, thinking about a single sample t-test, which is very similar to doing a confidence interval and comparing one value, a known value to it, it looks to me like this machine, with at least 95% certainty, is making up doses that are different than the machine we used to use, which over many years produced an average of 800. So it does look different, right? So we feel that the real mean for the new machine is somewhere between 754 and 786, quite different than the 800 for the old machine. But let's now use a different technique to do basically the same thing. We're going to do a t-test now. Okay, and the difference between a t-test now is we're going to set up a hypothesis. Okay, let me get rid of this. Okay. Number 14, nutritionists prepare, blah, 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 same problem. Using the new equipment, perform a single sample t-test, comparing the sample mean for the new equipment to the mean of the previous measurements, and so on and so forth. Well, what was our calculation for the t-value for a single sample t-test? It's simple. When we get into two sample t-tests, it gets complicated because we have to either calculate a pooled standard deviation, or we have to do some special gymnastics to determine the degrees of freedom if we assume they're not equal standard deviations in the two groups that we sampled. But for single sample t-test, it stays pretty simple. The t-score is equal to the difference between the two means, x bar 1 minus x bar 2, over the standard error. Okay, and how do we calculate our standard error? Again, we calculated it before, just the way we calculated it before. It's going to be, and since there's only a single sample, it's going to be the same standard error we had before. And standard error is equal to 30, because we know the standard deviation from only one sample. We don't know the standard deviation for the other machine, over the square root of the sample size, which is 16, and that comes out to be 7.5. So we know the standard error. Okay, so now we got to calculate our t-score. So our t-score is going to be the difference between the. Actually, I shouldn't call this. The x bar minus 1, x bar 1 minus x bar 2, because in one case we know the true mean, don't we? Right? So in our sample, x bar was 770. The true mean for the other machine was 800 over 7.5. So what is t equal to? T is equal to, let's see, we got 7, that's 30, minus 30 over 7.5, and that's equal to minus 4. So our t-score is minus 4. Well, if I look at my t-table for sample size of 16, 15 degrees of freedom, right, I know that my critical value for t critical, is 2.131. So since my t value, it doesn't matter if it's positive or negative. Negative just means it's 4 standard errors to the left rather than 4 standard errors to the right. So it doesn't matter if you figure it to be minus 4 or plus 4. It's the same result. Our critical value is 2.31. Since the t that we calculated for the difference between the mean of our sample and the mean of the population we're comparing it to, since that's greater than 2.31, we reject our null hypothesis and accept our alternative hypothesis. Of course, in real practice, you would always state your null hypothesis first. It's that mu1 is equal to mu2. We know mu2. And or you could just simply say that since we know mu2 is 800, you could have just said mu1 is equal to 800. That's our null hypothesis. In this case, it didn't come out to be an 800, so we accept our alternative hypothesis that mu1 is not equal to 800. So you could have stated it either way. Mu1 is equal to mu2, or mu1 is equal to 800, since we know what mu2 is. You could have just substituted the 800 for it. Okay, so that's basically what we did there. And I think almost all of you guys got that right. Most of you guys got the idea or were able to apply the formula and so on and so forth for the t-test. True, false. Based on the above result, you reject the null hypothesis. That's true. Okay, this one's a file response. We asked you to do a single sample t-test using SPSS. Okay, and we can quickly do that. I have the data file on the desktop. Somewhere on the desktop. Let's see. I'm working on the homework right now. I should have that up soon. And also, I already converted the 2 videos, so they're being uploaded to YouTube as we speak. That's from last night I'm referring to. Here it is, high school female athletes. And the question we asked was, in 1990, a large survey of high school female athletes found a BMI of 24. You believe that the BMI of current high school female athletes has changed. You have resources, form a sample of 56. And notice I said a large survey of high school female athletes. The reason why I said that is because I want to give you a justification for calling this the mean of the population of high school female athletes. Well, in other words, a survey of all female athletes. And since we now want to compare them to female athletes in the year 2015, well, now maybe we don't have resources to survey every one of them. We can only have the resources to survey a sample size of 56. Random sample size of 56. And now we're dealing with a sample versus a known mean, x bar minus mu for our t-test. In fact, our null hypothesis here is that mu in 1990, the mean BMI in 1990, mu in 1990 is equal to mu for 2015. Okay, or another way of saying it, since we know what 1990 was, mu for 2015 is equal to 24. Just put in that number. Or the alternative that they're not equal. Okay, so hopefully it's opened up. State your null and alternative hypothesis. We just did that. Use SPSS to calculate a 95% confidence interval for the BMI of 2015 athletes and report it in a Word document. Perform a single sample t-test, copy and paste of the sample, the SPSS, and report your conclusions regard to your null hypothesis. Okay, so let's see if it's opened up. It's still bouncing around. It's probably pretty close by this time. Should be open in a moment. Okay, and that's the last question. You would just be simply uploading that. Okay, and this is really is the foundation for all the stuff that goes on beyond this, for our two sample t-test, for our analysis of variance, and so on and so forth. Okay, here we go. All right, so let's take, there's only a single variable here, the BMI for the 56 students. Okay, here's our 56 students with their BMIs. I'm going to go to Analyze. Remember, it asks us for the 95% confidence interval. Well, that's hidden here in descriptive statistics. I can go into descriptive statistics, not descriptives, but explore. We need to go into a little bit more depth. Okay, correct answer to, I think you missed one there, right? I just noticed a question. Question A, what was the correct? I'll get back to 15 after I do this, just to make sure we know what the answer was. Okay, so I'm going to move the BMI into our dependence list. This is an explore. If I did dependence, it wouldn't give me a 95% confidence interval. I'll click OK, and it will give us the result for this collection of numbers. The mean happens to be 22.93, a little under 23. The 95% confidence interval for the true mean for BMIs for all female athletes between in 2015 is it's between 22 and 23.86, right? That is our 95% confidence interval. How did they get that? Well, they got that by taking the true mean and adding and subtracting, I'm going to say for the moment 1.96 times the standard error. And look here, SPSS even calculated the standard error based on the standard deviation of the population and the sample size, right? So it actually calculated. So it took that, multiplied it by 1.96, and added it and subtracted from that mean in order to get this range of 95% confidence interval. I told a little white lie there. Anybody know what the white lie was that I just told? Anybody catch it? It didn't really take 1.96 times the standard error, did it? The sample size is 56. SPSS never uses the z-score for a sample. It always uses the t-score, no matter how big the sample is. So my guess is it was really took 1.97 or 1.98, multiplied it by the standard error, and added it and subtracted it from the 22.9. Okay, get it? You guys get that? That like SPSS has the liberty to, like not take shortcuts and not use the t-test, even though it's a fairly large sample. Okay, so you would just copy and paste this into Blackboard. Let me go back and take a look at problem number 15, so I make sure that you actually got the answer to that one. Where did it go? Where did it go? Number 15 was what's the critical value? Yeah, the critical value is 2.31. The sample size is 16, right? So if you go to the t-table, and I'll like who is it? Neil requested this. I'll post somewhere like a folder on Blackboard where you can go and get a reference folder or something like that, where you can get all the tables and stuff like that. So you got them in one spot. So for 15, for 95% confidence, in other words, an alpha of 5% or 2.5% in each tail for a two-tail test. All of these are ways of describing it. For a sample size of 16, 15 degrees of freedom, we would use 2.131. If I wanted to be 99% certain and was willing to only have an alpha of 1%, well then the T critical would have been 2.97947. Type 1 and type 2 errors again? Okay. All right. Type 1 and type 2 errors. Okay, let me just get back to my notebook here. I'll end up with that, and I'll be posting a time for this weekend where we can get together and spend some time preparing for the exam. And again, I'm going to get a homework up so that you can give the problems a try, so you can use it kind of a combination of homework and a prep for the exam. T-table. Let me try notebook. Let me get my notebook. Okay. Okay. So now I'm going to write a couple of hypotheses down here. A null hypothesis and an alternative hypothesis. Okay. Let's say that my null hypothesis is that the mean let me think about this for a second. What's a good one? What's a good hypothesis that will make it easy to illustrate this? That the mean blood pressure for males is equal to the mean blood pressure for females. Okay, this is a rant. We're going to take a sample of males and females in the age range of say 50 to 70, right? In the borough of Brooklyn, they're gonna come from the borough of Brooklyn. They're gonna have an income range from 30,000 to 50,000. They're gonna have a BMI of a normal BMI, whatever that is, like I guess maybe 20 to 25. And we're gonna get a fairly narrow range of qualifiers here. So, but I'm gonna say that I'm gonna get this group of males and females, right? And I'm going to say, gee, I think males have a naturally higher blood pressure than females of the same age, economic category, and so on and so forth. I want to test that hypothesis. So the way I test that hypothesis, I want to prove that males have a higher blood pressure than females, or at least a different blood pressure, for argument's sake. So the way I do this is I start with the assumption, the opposite of what I'm trying to prove, that there's no difference. Male blood pressure is equal to female blood pressure. Okay, my alternative hypothesis is that they are different, that blood pressure for males is not equal to blood pressure for females. So my objective is to be able to reject the null hypothesis, reject this idea that they're equal, and accept my alternative hypothesis. Okay, so let's say I do my statistics, I calculate my z-score, and I do my t-tests, and I do my whatever it is tests that I use, and I say, I reject my null hypothesis. I have enough evidence to be at least 95% certain that I can reject my null hypothesis and accept my alternative hypothesis, right? Well, we're saying that we're 95%. We only need to be 95% certain. That means that you're willing to accept a certain level of risk, in this case 5%, that you could be wrong when you reject that null hypothesis. Well, if you reject the null hypothesis and say that I accept the alternative that there is a difference, when in fact in the real, remember we're doing this on the basis of samples, in the real population, in the real world, it turns out there's no difference. You just said, oh, males have a higher blood pressure than females. That's a type 1 error. When you incorrectly reject the null hypothesis, that's a type 1 error. That's a bad error. Why is that a bad error? Because now doctors will say, I don't have to worry about female blood pressures. I really should focus on male blood pressures, and I'll let females worry about themselves because, in general, they have lower. We have a study from the PH750 classes summer of 2015 that tells us that male blood pressure is the real problem, not females. Male blood pressure higher than females. So I'm going to concentrate on males and I'll disregard females when I treat them. That's a type 1 error. That's a bad error. If a male comes in here, I'm going to test his blood pressure for sure and give him drugs to correct it, but I'm not going to worry about females. That's a type 1 error. That's a bad error, right? You don't want to make that kind of error. Okay, now let's say that you do a study, and in fact, there is a difference. Males have a different blood pressure than females, but you don't get enough evidence. Your p-value is 0.07. You don't have enough evidence to quite reject the null hypothesis. So you fail to reject the null hypothesis, when in fact there is a real difference. Well, what is that? What's the result of that? Well, the result of that is that, somebody had a very interesting study. It suggested that almost to about 7% chance of error, in other words, 93% certainty, it suggested that there was a difference between male and female blood pressures but they didn't really have enough data to really reject the null hypothesis, right? But there is a difference, and they failed to find that. They failed to prove that difference. That's a type 2 error. Okay, that one's not so bad because that one usually winds up with some evidence that suggests, like at least a trend that you can see that suggests the data suggests that males have higher blood pressure than females do, but you weren't able to prove it. So now someone else, now at this stage, you haven't made the assumption that this is true. You haven't accepted this to be true. That's why we don't say we accept the we accept the null hypothesis when we don't have enough evidence to reject. We just say we fail to reject because you're not really accepting that. So you're not really making that big an error. You just don't have enough evidence to come up with the right answer that there is a difference. That's a type 2 error. Okay, I hope that helps. Okay, so at any rate, guys, let's call it a night, and I'll post again. I'll get the homeworks up and post again, get videos up tonight, and we'll get together again and go over some material for the final, and then we'll, from there on next week we can really concentrate on the projects and stuff like that. Have a good night, guys. Bye.